Oh, let me record. This is 3.3, yes. As promised, we saw this not too long ago, and I told you we would come back to it whenever we get to imaginary numbers, and so here we are. Yeah. So welcome to the world of imaginary numbers and math. All right, so here's what you have to understand complex numbers. You first have to understand imaginary numbers. So big title of this lesson is complex, but we're going to start with imaginary. Now, this has to do with radicals. And so my first question to you is, when you have a radical, meaning a square root, what can't happen there? You know something. You can't have a negative under the radical, right? Because the definition of that square root is what multiplies by itself twice to get what's under here, right? And if you have a negative number, you can't multiply the same thing 2 times and get a negative number, right? Does that make sense to you? So I can't do the square root of -4 because there are no 2 numbers that multiply to -4 if they're exactly the same. Does that make sense to you? Do what? No. Different, no. All right, so, but what we are going to do is we're going to use imaginary numbers. So if I told you that the square root of -1, because everybody always says imaginary, what? A good moon?
You wasn't this morning when I walked in. You like Lily.
I'm in pain. My head hurts so bad, so it's odd that you say that I am. I seem what? Yeah. I'm trying not to. Yeah. That's an I. Okay. So the square root of -1, we're gonna let that be I. So if we think about the way radicals work, remember we talked about simplifying radicals where we could break it into 2, right? That wasn't it. Okay, so last year, like, let me digress just a second then. Let me sidetrack here, and then I'll go back to that. If you have a radical, okay, let's say I have the square root of 18. Go ahead. What I can do, because radicals have this special property that if you multiply under the radical, you can split them up separately. Okay? So what I do is I look at what's under the radical here, and I say, okay, is there a perfect square that 18 is divisible by? Okay, and I want the biggest perfect square, 9, right? Because we all agree that 9 times 2 is the same thing as 18, right? And then, so I could break that up as the square root of 9 and the square root of 2 by this property.
Aren't you gonna do like...
You remember doing this?
Because I understood this.
3 square root 2, and I throw a plus or minus in front of it because a square root can be positive or negative,
I think
right?
I didn't fail this test.
Okay. Okay, so if you did it good, you remember. If you didn't, I hope this clarifies a little bit. So you'll know you're done when you look at what's under the radical and you can't divide it by any other perfect square. What's the square root of 9? Okay, so sometimes as I work these, I'll have a list of perfect squares over to the side, or at least whenever I teach students how to do this initially. Maybe I list out some perfect squares over to the side. And I say, what's the biggest one from this list that I can divide what's under the radical by? And then I split them up. Okay. Let me show you one more, see if you can do it. Let's see if you understand. Simplify that radical. 25 and 3, because of all the perfect squares you know, 25 is the biggest one that'll go in there evenly. So I would have, and I always do this little number to know that we're splitting them up. So this is square root 25, square root 3, 5 square root 3, right? And I do the plus or minus out in front. Okay? We're going to use that property as we do complex and imaginary numbers. While I'm here going over radical properties, I don't want to, yeah. No, 25 times 3 is 75. It just can't be divisible by another perfect square. And that's how, if you can be, then you keep going with the process. Correct, you need to do it again. So if you had something like, let's say I had 3 times the square root of, what'd you say, 50? This one, I would need to do this again here. So I've got 3 on the outside, square root of 25, square root of 2. Square root of 25 is 5, so this is a multiply. So 15 times the square root of 2. Yeah. 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 All right, so that's one of the radical properties that is assumed that you know. I didn't realize we didn't know that, so it's okay. It's all good. It's okay, yeah. We used to teach it in algebra too. The other one that you have probably heard of at some point, but you may not remember, if you have, it goes along with dividing. If we're dividing, okay, it also goes top and bottom. Now, this doesn't work when you're adding or subtracting, but only when you're multiplying and dividing. But here's the problem. I can't have the radical in the bottom of the fraction. So I have to do what it's called rationalizing the denominator. Okay? In other words, I come here, and if I multiply by what the radical is in the bottom, so if I multiply by the square root of b, and because I'm multiplying, it does just become b. Okay? Because I'm multiplying, as long as I multiply by something that is the same top and bottom, that's like multiplying by 1, and so the value stays the same, right? Multiply anything by 1, its value stays the same. Anything divided by itself is 1. So up top, I end up with the square root of a times b. And on the bottom, you're absolutely right, it would just be b. Does that make sense to everybody?
The same numbers cancel each other out.
Well, because if you do square root of b times square root of b, if you put them together, so the backwards of that property, that would be the square root of b squared. And these are opposites. Cancel each other out. There's your b.
Like halves.
Yeah.
Like if the square root of something is half of the
Does that have to be a variable?
No, it can definitely be a number. That's just a generalized. So if I had, let's say I had 3 square root of 2 over square root of 5. Okay? So I would need to multiply the top and the bottom by the square root of 5 because the problem is the radical in the bottom. You can have radicals in the top all day long. So up top, I end up with 3 times the square root of 10. And on the bottom, what do you get? And this is plus or minus. Okay. Okay, so sorry for the digression. You okay? Is the baby okay?
I'm not.
I'm sorry.
Listen to my now.
It probably has a sensor in the back to make sure that you're patting the back.
I put tape over the speaker. I don't know if you heard that.
You put what?
I put tape over the speaker. Oh! You did
I'm going to hit record again. All right, baby's happy now. We're good. Let's go back to imaginary numbers now. So we talked about you can't have it on the bottom. You also can't have the negative under. So we use imaginary numbers if we have a negative under the radical, okay? So what we do is we let the square root of -1 be I. Okay? So if I had the square root of -4, which is what we were looking at a minute ago, if you think of this as being really the square root of -1 times the square root of 4. Well, what is the square root of -1? I. What's the square root of 4? 2, right? And I'm just going to rewrite this so that it's in a prettier form, and I'm going to say 2i. In general, if you have a radical, you put the I in front. If you have a whole number, you put the I following it, kind of like you would any other variable if it was an x.
If it's like 5, you just do square root of 5.
So if you had the square root of -5, okay, that's like the square root of -1 and the square root of 5. you'd leave the I in front of the radical here and make sure you put that plus or minus out front. So it'd be I times square root of 5. Okay? It's really not a hard concept. Basically, when you get to go in with it, I like to show you why. But you basically just drop this negative sign and throw an I outside, and it works. Okay.
So the only one that's imaginary is negative 1.
Yes, because of the negative. So let's look at this one because I want you to simplify. If I asked you to simplify the square root of negative 216. Okay, so we got several properties we got going on here that we got to take care of. Very first thing, this negative got to go, right? So I'm just going to do this. Does that make sense? All right. Now I can split this 216 up if there's a perfect square. All right, but 12 is not a perfect square and 18 is not a perfect square. But 6, so 36. You see what I'm saying? You're looking for the squared numbers.
So how can you get these numbers faster? You just have to try.
You have to try them. That's what I said. And until you're really comfortable with doing this, you might have a list of perfect squares. 3, 4, 5, 6, 7, 8, and so on. Okay? And you want the biggest one that will go into it. And this is 36. 36 times what is 216? 36 and 6. 36 is the one that simplifies down. So this becomes plus or minus 6I root 6. Just general pretty math always puts the whole numbers followed by the variable, and then if there's any other operations left, they come after. It's just. But 3 is not a perfect square. It's got to be a perfect square. If you use it, it needs to be a perfect square so that you can simplify it down. At the point that you can't divide this by any other number on that list, then you're done. Okay? And if you don't pick the biggest one to start with, it's okay. You can keep going from there. All right, so we do some operations with imaginary numbers. Let's talk about addition and subtraction first because it's the easiest. Addition, subtraction of imaginaries. This is the easiest thing. If they're already imaginary numbers, so let's say 5I plus 2I. What do you think you do? Well, how do you combine those? 7I. It's no, it's just like any other. You just literally combine like terms. If that was 5x plus 2x, what would you do? Yeah, you do the exact same thing. So this would be 7I. Yeah. We're going to talk about multiplication is different. Okay, so what if it's 2I minus 5I? It's okay, it's okay. Sure, it can. So this will be negative 3I. You're literally just combining the coefficients in front when you add or subtract. Yes, yes. Yes, ma'am. It would be like 2 times the square root of negative 1. Other questions, addition, subtraction? Yes, we will.
We're going to like backward and out, backwards.
No.
So we don't have to take like 5I to whatever it was before. Negative
No. That would be the square root of negative 25, but no, you won't have to do that. All right, and we're going to talk about all the operations with imaginary, then we got to move on to complex and talk about those operations, okay? So y'all stay with me. All right, so that's addition, subtraction. Let's do multiplication. 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 So someone's already said, I think Callie said, would you just get I squared if you multiplied them? And you would, but I want you to think about something with me for just a minute. If I is the square root of -1, what do you think happens when you square I? Close.
-1.
It's -1. Here's why. If you square the square root, these are opposite operations, right? They cancel each other out. All right, so it leaves me with just -1. So if you see I squared, you know, hey, that's -1. So what if I saw 6I squared? What does that become? -6. 6 times -1, which is -6. So if you see an I squared, it's not really an imaginary number anymore.
So, it would be a negative of that number.
Correct. What if it was negative to start with? What if I had -5I squared? It would be +5. So in general, what happens is I squared changes the sign and goes away. Okay, do you see why? I squared is -1. If you multiply anything by -1, it just changes the sign of the number. Okay? So I show you all that so that I can show you multiplication of imaginary numbers. What if I had, I want to use different, why does your brain always go to the same numbers every time?
12.
12. 12I times -14I. Thank you. So if I'm multiplying these two imaginary numbers, what do you do? And think about them if they were x's, because you're going to do the same thing. What do you do when you're multiplying? Multiply the coefficients. So what is 12 times -14? Okay, -168. And then I squared. Exactly. Easy? Because you're multiplying two i's together. Yep. Okay. We won't get there.
And the I squared changes the sign to positive.
Correct. Okay. What about division? Now remember, we're only dealing with imaginary right now, so when there's just an I, okay? What is the problem here? It's in the bottom. What's in the bottom? The I. And an I is a radical, and I can't have a radical in the bottom.
So it's not a function.
Yes, y'all are right. Y'all are right. So I multiply the top and the bottom. Remember, if I've got a radical in the bottom, I just multiply the top and the bottom by that radical, right? Well, essentially, it's just I.
That's 5I over -2.
Look at you go, Adele. 5 over 2I squared, and if you ever see an I squared, drop it off, change the sign of the number. Oh, I forgot my I up here. 5I over -2. Easy enough? Because it's going to get a little...
What does this do?
We're simplifying right now. I'm fixing to show you. We're going to solve... You know how we've been solving quadratics by graphing? We're going to solve... Huh? Anytime you see an I squared, drop it and change the sign of the number. Because I squared is -1. Well, if the I is in the bottom, then you multiply the top and the bottom by I. So whenever I have 2, well, you leave the I up top. Because it didn't have one to start with. Okay? So when are we going to use this? What use is this for us? Remember, I started this telling you complex numbers, and we haven't gotten there yet. Okay, so y'all stay with me. Before we do, let me show you a couple examples like this. We have solved by graphing, right, where we found those places where it crossed the x-axis. Remember that? But we said sometimes there are some scenarios that happen where it never crosses the x-axis. I can still have two solutions, but they're going to be two imaginary solutions. Okay?
Is it like
So, well, we're not going to graph on an imaginary plane. We'll just, but let me show you. If you have something like x squared plus 25, that's my number of the day, equals 0, okay? Now, what we've done so far is we graph that, we look at where it crosses the x-axis, and we find those zeros, right? But when I graph it, I get something that looks like this that's not intersecting the x-axis, okay? Now, here's one thing I say in Algebra 2 all the time, and in pre-cal and every class I teach. If you're solving algebraically, okay, if you're asked to solve something algebraically, and you look at your equation, no matter how complicated it is, if you only see x written one time in the equation, you can always sad map your way out of that.
What's that? The
Okay.
Opposite.
the opposite stuff.
Haven't we talked about that before?
Yes, ma'am.
You kept saying it, we didn't know what it was.
So it's the order in which you solve an equation, okay? And if you ever see x written only one time, you can use that method to solve every single time. And you're going to see throughout this chapter, we're going to talk about different methods of solving, okay? And this is an easy method of solving that you want to use if you ever can. So looking at this, what's the first thing you would do to get x by itself? Subtract 25. So I have x squared equals negative 25. And then square root, and you see where I'm getting with this. But it's plus or minus 5i. Yeah. Well, because this is a property of square roots, but this is not.
Well, why did you put the I?
Because it's a negative under the radical. So any negative under the radical gives me an I. One more? Oh, hold on, I don't want to do that one. That's going to be 5 again. Solve for x. Don't look up at the board until you finish because I'm quietly working it out as you do. It's 10:36. Oh, 26. Sorry. Because the square root of -1 is I. If there's a square root under the radical, you drop it and put an I outside every single time, without question. Because we can't have a negative under the radical. All right, that's half the lesson. Square root 36. All right, now we get to what we were trying to get to. Well, that's part of it. But we started out with a heading of complex numbers, and I jumped into imaginary numbers, right? All right, y'all got to stay with me. Complex numbers. Uh-oh, you better get some more. No. cancel. Complex numbers are made up of two things, and they're a really easy concept. It's the operations, just a couple of the operations with complex numbers that throw us. Complex numbers are made up of two parts. They are a real number, and then you either add or subtract an imaginary number to it. That's not a hashtag, all you social media people. All right, so maybe it's 2 plus 3i. 7 minus 8i. 1 plus I. Okay, any of those are complex numbers. They have two parts. If you're missing the real part, then it's just an imaginary number. Okay, and a couple of the little rules change a little bit. But if you're talking about complex, it's got two parts, a real part and an imaginary part. Okay, so we're going to talk about the operations with complex numbers and we'll be done. Addition and subtraction are the easiest, as usual. Let's say I have two complex numbers. 3 plus 5i, because clearly those are the numbers of the day, plus 2 minus 7i. If you need to add those together, what do you think you do? Oh, come on, y'all, add. If this was multiplying, we would FOIL. Y'all would be right. Everybody said that in unison. But for this one, because I'm adding, so watch these. And it's good that y'all said that, because on the test, everybody always gets confused and starts FOILing because you see two sets of parentheses. But you have to check that operation carefully. Adding just means, again, we're still just combining like terms. So look at what goes together. 3 and 2 and 5i and negative 7i. Does that make sense? It's adding numbers and adding imaginaries. Combine like terms. Now, if I had changed this around to subtraction, I'd have a little bit different problem. Minus, what was it? What did I have? 2 minus 7i. Because I'm subtracting everything in the parentheses, really I'm adding the opposite of everything. You know how you did same, change before? You probably learned that whenever you learned to subtract way back when. This is like a same, change everything that follows the subtraction sign in parentheses. Same, change everything. Everything in that parentheses is being subtracted. And once you... Huh? Mm-hmm. Yep. And listen, if there was something else over here on the end, like if I had plus 5, I wouldn't change that sign. I only change the ones that are in the parentheses that follow that subtraction sign. Yes, it groups them together is exactly what it's doing. What you're really doing is it's like saying that there's a negative 1 out here that's distributing through to everything. Okay, so now I just gather my like terms together. 3 and negative 2 is 5 and 7i is... Am I going too fast through this? Okay, because this is pretty... Okay.
Does it get harder?
Yes.
Okay.
Let's do what y'all wanted to do. Let's take these same two complex numbers and let's multiply them. So let's take the 3 plus 5i times 2 minus 7i. And yes, you are right, this is a FOIL problem. I'm not a big fan of the word FOIL because it only works when you got two binomials, but I like distribute better. This term has to multiply to everything in this parentheses, then this term has to multiply to everything in this parentheses, right? If I had another one, I'd keep going distributing through. So, 3 3 times 2 is 6. Let me write it down here below it. 3 times negative 7i is 5i times 2. And 5i times negative 7i. Negative 35i squared. So here, watch what I'm fixing to do. Exactly. This is just a positive 35. I squared goes away, changes the sign of the number. Okay? So what I really have, remember a complex number is the real number and then the imaginary part. So real number part, I've got a 6 and a 35, which gives me what? Y'all can do that. 41. And then, you're exactly right, minus 11:15. End or start? Oh. 12 or 5.
Actually, I'm saying, let me see there.
Oh, wait. I said, oh, you shut up. And I realized
If you have a what? We won't do that with imaginaries. Okay, so if that was x squared, it wouldn't go away. Since it's I squared, it goes away and becomes negative 1. All right, let me get to the hardest one, which is division. And here's why this is a problem. Same two complex numbers. The problem is because that I is in the bottom again, right? But if I multiply the top and the bottom by I, does the I go away?
Yes.
Does it?
Wait, if you I squared, does that make it negative?
It just makes it 2i.
Don't write this down. But look what happens. I have 3i plus 5i squared. I don't really care what's going on in the top because that's a moot point. I'm looking at the bottom to see. 2i minus 7i squared. Look, I still have an I in the bottom. That did not resolve the problem.
Can you somehow square the I?
But the I, yeah.
So I'm going to tell y'all what to do. You should have rationalized denominators with radicals at some point, but if you didn't, and I'm going to assume you didn't. When you are adding or subtracting with a radical, you can multiply by something called the conjugate. The conjugate is a big fancy word for a really easy concept, okay? The conjugate of a complex number is just the exact same thing, but with the sign in the middle changed. Okay, so conjugate just means change the middle sign. Now remember, if I'm multiplying, then I have to do the same to the top and the bottom so that I'm really just multiplying by 1. So then I would have to do the top also, 2 plus 7i. But multiply that out in the bottom and watch what happens. It's really kind of cool because you don't expect it.
Wait,
I'm going to do the top first. 6. Change the middle sign. Yep. You got to multiply the same thing on the top and the bottom. And remember the top, I'm not really concerned if an I stays there or
so you're
not.
multiplying the whole bottom of the and the whole bottom of the bottom.
You got to multiply the same thing top and bottom because anything divided by itself is 1. Yeah, the whole thing. All right, so we're going to multiply it out. 6 plus 3 times 7 is 21. 5i times 2 is 10i. Plus 35i squared. Now the top doesn't matter. There's going to be some i's in there. I don't care about that. The whole reason I multiplied by the conjugate of the bottom was to get the i's out of the bottom. So let's see if it worked. 2 times 2 is 2 times 7i. Negative 7i times 2.
Oh.
Ah. minus 49I squared. Look what happened.
You can
It's
get
crazy,
rid of
right? The middle terms,
that becomes 49.
I go ahead while I'm at this step and change all my I squareds. This becomes negative 35. This becomes positive
So
49.
you change the sign?
Yes.
Oh, I thought you just got rid of it. Two and change the column.
You change the sign. You have to change the sign. So up top, I end up with, what's 6 and negative 35? Negative 29. 31I. And then down on the bottom, conveniently enough, my I's are gone, which is what I wanted. That was the goal. So I'm just left with the 4 at the front and a 49 at the back, which is,
So why can't you just multiply by the i's and then get 7?
if you just multiplied by the I's up top, it wouldn't go away. You'd have 2I minus 7I squared on the bottom. Yes, but the 2 would have an I hooked to it. Like you can't just multiply one term. You'd have to multiply everything on the bottom. Yes or no?
That's the hard one.
Oh,
Yes.
now,
Oh, okay.
now it is. You delete or
Do you need another one?
or
Pretty good with this. I'm hearing a consensus of it's easy.
Is there one problem?
So the only type of word problems there are, it says the current in one part of a series circuit is 5 minus 3J amps. The current in another part of the circuit is 7 plus 9J amps. Add these complex numbers to find the total current. So it's literally given there for you. It's nothing too hard.
wait, is it 2 plus 6 here or is it 2 plus 2?
It would be 12 plus 6J. All right.